Hello, everybody. We're moving on now after the second midterm exam into hypothesis testing and conclusions about population parameters, where we're looking at two independent populations now. So here we're going to be looking at two proportions, and what we're actually testing is we're comparing two sample proportions, but we're really testing the difference between those two proportions. So the key concept in this method is we're making a claim about those two proportions. Now we're calculating the difference between the two sample proportions and using that to draw a conclusion. This can be done, we can use sample proportions or population proportions, or, since it's also in a decimal form, we can use probabilities or the decimal equivalent of a percent. So if we're taking inferences about two proportions, there's two ways we can go about it. We can do a hypothesis test, which is going to be the first method we're going to look at. Or we can use that confidence interval idea. Now, remember, we said the confidence intervals for proportions, the basic intervals that we use, the walled intervals that we use in this textbook, are not totally dead on to the percentage that they're given. If it's a 95% confidence interval, it's not going to be accurate exactly 95% of the time. With the intervals for the mean, if it's a 95% interval, it's going to be accurate 95% of the time. So there's a slight difference between the confidence interval and the hypothesis testing methods for proportions. So some of our notation that we need to make sure we're looking at here. So for the first population, remember we're comparing two populations here. P1 is the population proportion. Of course, we don't know that because that's what we're trying to estimate in our tests. N1 is the size of the sample from population 1. And X1 is the number of successes in that first sample. So P hat 1 is the sample proportion, so that's X1 divided by N1. And Q hat 1 is just 1 minus P hat 1. It's the complement of the sample proportion for sample 1. And then, of course, for population 2, we do all those again, just with a 2 instead of a 1. When we're making inferences about two proportions, we need some way to combine the two of them when we're calculating our variance. Remember, the variance for a proportion was the square root of P times Q over N. Well, now that we have two populations and two samples, we have to combine those proportions. And we do that using something called P bar. And P bar is just the number of successes in sample 1 plus the number of successes in sample 2 over the size of sample 1 plus the size of sample 2. An alternative of this is sometimes do N1 times P1 plus N1 times P2, or N2 times P2 over N1 plus N2. So if you're not actually given the amounts of successes in each sample, you can do the sample size times the proportion to estimate those number of successes. Then, of course, Q bar is just 1 minus P bar. That is what we will use in our formulas whenever it's called for the population proportion. So now, to make our inferences about two samples, we have conditions that have to be met, requirements that we have to meet. Two samples must be simple random samples, and they must be independent and from the desired populations. Now, independent here means a couple of things. One is it means the two populations don't have any overlap, for one. Second, it must mean that there isn't a logical pairing between the two samples in any way. And then, just like we had to have for other intervals and tests, we must reasonably expect to have at least 5 failures and 5 successes. So then our test statistic is right here. The difference between the two sample proportions minus the hypothesized difference in the population proportion. Remember, this comes from that null hypothesis from HO. Over, this is our standard error of the sample proportions. Remember, we said for one sample, that standard error was the square root of P times Q over N. Now that we're looking at two samples, we combine them using this, where that P bar and Q bar are that pooled proportion from up here. So to make our inferences, for the hypothesis testing, we have two different methods. We do a p-value method or a critical value method. Both of them involve either using A2. Now, since we don't have a hard copy of the textbook, it's a little tough to look up A2. Some questions in MyMathLab will give you a link to that table. Remember, we saw one in Chapter 8 that had that link. I said it'd be a good idea to write down that question number and that assignment number so you can refer to it if you want to. What I always do is once I've pulled up that table once, I just leave it up on my computer screen so I always have it. So even in a problem where it's not linked, if I want to use it for something, I have it there. But we can also use Excel and StatCrunch for those things as well. Then we also have the confidence interval. Like we said, this is going to be slightly different. Most of the time it's going to agree with our p-value and critical value methods, but there's a small percentage of the time where it's going to be slightly different. But we do have the same method of creating that confidence interval. We have to find a margin of error, and then from our estimate of the difference, the point estimate, we add and subtract that margin of error. So this is just reiterating that the p-value method and the critical value method will always give the same result. They will always be equivalent. But that confidence interval method is not quite exactly the same. Because remember, we said the standard walled confidence interval for proportions is not totally true to the percentages given. So in our hypothesis test, first of all, the null hypothesis is usually stated as P1 is equal to P2, although it could be really less than equal to, greater than or equal to. If this were a more in-depth course, we'd use P1 minus P2, because that's really what we're testing is the difference between those two. And then we could use a value. When we say they're equal, we're saying that value of that difference is 0. But in a little bit more advanced course, we might look at, hey, maybe it's 10% larger. Maybe the difference is 0.1 or whatever. For this class, we're always going to assume that difference is 0. In other words, that P1 equals P2. It simplifies the calculations a lot. Because of that, then we can use that pooled proportion, that P bar that we saw a few slides ago, the x1 plus x2 over n1 plus n2. So let's look at an example here of the rates of e-cigarettes and nicotine replacement for success for people who want to try to stop smoking. So we've taken two samples here. One group is people that used e-cigarettes to try to stop smoking, and out of that group, 79 out of 438 were successful to stop smoking, or a 0.180 proportion. In the nicotine replacement group, 44 out of 446 were successful in stopping smoking, or a proportion of 0.099. Now, you might be looking at those and saying those proportions are way different. So it looks like there's a difference, and it does look like there's a difference, but we need to confirm that with the test. Remember, there can be a slight difference that's just caused by random variations in the random sampling that we selected. So we have to test to see if that difference is big enough that we can consider it statistically significant. So we're going to test at an alpha of 0.05. So alpha is 0.05. So if we get a p-value of less than 0.05, we would reject the null hypothesis. Or we can also use that alpha to find a critical value. So let's check our requirements before we go any further. First of all, these are random samples from their desired populations. Second, the samples are independent. There's no overlap between the populations, and there's no link from one sample to the next. And there's obviously more than 5 successes. We had 44 in one and 79 in the other. And if we subtract from the total, there's definitely more than 5 failures there as well. So we have met that requirement pretty easily. So if they plug the information into XLStat, this is what it spits out as this display here. I can't put XLStat on my computer because I don't have administrative rights to install that, but you should have that at home. But I'm going to use StatCrunch. I like StatCrunch because it is included right in the MyMathLab software, so you don't have to install the add-in on your computer. From the MyMathLab's homepage here, once we're in the course, you just click on StatCrunch here. StatCrunch website. And then open StatCrunch. I know there's a few clicks there, but then we get to StatCrunch. Looks a lot like Excel, only it works way better. So we're going to go to Stat, and we're going to go down to Proportion Statistics here. And this is 2 sample. We're testing 2 populations. We do not have a list of the individual responses. We have the summary data, summary statistics for each of the samples. So we go with summary. Now, the number of successes for the first was 79 out of 438. For the second, there was 44 successes out of 446. So then next we have to select that we are doing a hypothesis test, and it's of the form P1 minus P2. That difference is 0. So saying that difference is 0, that's just saying that P1 equals P2. And then the alternative, we're going to go with not equal to for alternative. And we do want to show the critical value, so I'm going to make sure I click that. And alpha is 0.05. So if we hit compute, we get a little bit different looking display, but all the same information. This is just our information from our 2 samples. Here's the difference between those sample proportions. This is the standard error. This is our test statistic. We get 3.51 as our test statistic. Critical value is 1.960 and a p-value of 0.0004. So I'm pretty sure you can see where that's going for our conclusion here. Same information we got up here, only rounded off to a little bit different decimal places. Let's interpret this result. So since the p-value is less than 0.05, we have rejected the null hypothesis. So the proportions are not the same between these 2 different methods. Let's go through and calculate that now by hand to see what we get for results here. So the manual calculation, if we want to claim that there is no significance, so HO is P1 equals P2. The alternative then is P1 not equal to P2. So that's right down here. Those are hypotheses. Using the alpha of 0.05 level of significance, we need to pool our proportions. So what we're going to do on the calculator, we have to know how to enter our parentheses here to make this work. So on parentheses, we do 79 plus 44, close the parentheses, divided by, then put parentheses around the bottom, 438 plus 446, and then close those parentheses, and we get that pooled 0.1391 is that. Now, the slides here use that out to the full, 9 decimal places there. We don't have to go to 8 or 9 decimal places like that in our calculations. It should be just fine. Q then is just 1 minus P, and we get the 0.8609 there for Q. So because we assume in the null hypothesis that the proportions are equal, and therefore P1 minus P2 is 0, then we can use the P bar in this calculation. So we have proportion 1 minus proportion 2 minus, this is from the null hypothesis, remember that's 0, so we put 0 in there. And then we use that P bar and Q bar for our standard error. So the way we would enter this in the calculator is on top, we'd have parentheses, 79 divided by 438 minus 44 divided by 446. We close those parentheses, and then divided by, on bottom, we have to have the square root. So second square root, it gives us 1 open parentheses there, and that's actually all we need. 0.1391 times 0.8609. Notice I didn't go out all 8 decimal places. I only went 4. That should be more than enough. Divided by, and I didn't need parentheses around that on top, so divided by 438, and then plus 0.1391 times 0.8609 divided by 446. And now we do need to close the parentheses on the square root, and then hit enter. 3.51 is our test statistic, which is what we had from the StatCrunch readout. Now in the StatCrunch, it told us our critical value is 1.960 if we round it to 3 decimal places. What that's meaning, if I'm going to jump down here, that means that our cutoff here is 1.960 for this tail. That should be negative 1.960 over here. Anything out on this tail or out on this tail is in the rejection region or critical region. 3.51 is definitely out in that region, so we are going to reject the null hypothesis based on the critical value. So then for the p-value, we have to see what is the probability of being more extreme than that. And of course, the p-value is given in StatCrunch, gave us the p-value of 0.0004. Let's use Excel to just find the p-value here. So I use the normal distribution. Our x value here is 0.0004. There's a mean of 0, standard deviation of 1, and yes, we want cumulative. Oops, we got to put in true for cumulative, not yes. Now, that gave us the probability of being less than a positive 0.0004. That's the p-value. So I want to put in my 3.51 is my test statistic. Now this is going to give us the probability of being less than 3.51. Our p-value is the probability of being more than that, so it's 1 minus that number. And because it's two-tailed, we have to multiply that times 2. So we take that 0.2222 times 2 to get 0.000444, rounding off to 4.5. So there's our p-value. So again, here's back to the normal curve. We see that we are in the rejection region. Our p-value, again, we multiplied by 2 because this is a two-tailed test to get the p-value of 0.0004. We definitely reject the null hypothesis. And we need to word this now in such a way as it makes sense according to that null hypothesis. So reject the null hypothesis of the two proportions being equal. What this is saying is it appears that there is a significant difference between the proportions. Now here's a spot where this textbook gets sloppy. The alternative hypothesis is that the proportions are not equal. So to a technical statistician, that's as far as we can go with our conclusion. There is sufficient evidence to reject the null hypothesis, so we conclude the proportions are not equal. Well, this book goes on to say, well, it appears that the e-cigarette treatment is better than the nicotine replacement treatment. Yeah, the data does show that, but the test cannot conclude that because when we're doing a hypothesis test, we either fail to reject the null hypothesis, so we stay with it, or we reject the null hypothesis and we have to go with the alternative. And the alternative was that they were not equal. It was not saying that the e-cigarette treatment was better than the nicotine replacement treatment. So if we wanted to make that conclusion, we would have to go back and retest. We would have to change the test and use the hypotheses. HO is that the proportions are equal. And the alternative hypothesis would be that the P1 is better than P2. And then, of course, remember what that means is this really is saying P1 is less than P2, less than or equal to P2. Then we can conclude, if we reject the null hypothesis, that the e-cigarette treatment is better than the nicotine replacement treatment. So yes, this is saying that to verify that that is the case, we would have to go back and redo this as a one-tailed test. So the p-value would actually be even smaller with only one tail. And I'm not going to go through that process now, but you could go through that process and you could repeat it. Actually, let's go to StatCrunch. StatCrunch will do it really quickly, so let's go ahead and do that. So stat, proportions to sample, summary, 79 out of 438, 44 out of 446. And now we're going to make this less than here. Show the critical value. Notice when that is less than, our critical value changes a little bit. And actually, I didn't want that to be less than. I want it to be greater than. So let me try that again. Trying to go too fast, and I punched in the wrong thing there. This should be greater than. Still less than. And then we still want our significant or critical value. Our critical value is the same numbers, just positive now instead of negative. Test statistic doesn't change because we're still using the same data. The p-value changes, though, because it's only one-tailed. So the p-value now is only 0.0002, which is what they're saying here on the slide is that p-value is going to go down once we go to a one-tailed test. So, yes, we can eventually conclude that the e-cigarette treatment is better than nicotine replacement, but we would have to go through and redo that test in order to get to that conclusion. So the critical value method, as we said, the 3.51 is greater than the 1.96. So we can reject the null hypothesis because we are out in that critical region or that rejection region of our curve. If we want to use the confidence interval method, now remember, so the confidence interval method is not always going to match up. Now, since we rejected by quite a margin here in our hypothesis test, the confidence interval will match up with our hypothesis test here. We could use ExcelStat or we could use StatCrunch. Let's use StatCrunch and I'll show you how that works out in StatCrunch. So stat proportions to sample with summary. We put in our exact same data here as we did for the hypothesis test. But now we click down here, confidence interval with 0.95. We're going to 95%, and we'll show the critical value again just so we have it. And there's our interval. Going from 0.0363 to 0.1271. That's exactly what we got here if you were to use the ExcelStat in Excel. If I want to do this by hand, well, I have this formula here that is the margin of error. So that margin of error on the calculator, I do my critical value, 1.96. We got the critical value from ExcelStat times second square root. I do have to have parentheses here. 79 divided by 438 times 359 divided by 438. That's just my P and Q for P bar and Q bar, or sorry, P and Q for sample 1 divided by the size of sample 1, which is 438, plus parentheses 44 divided by 446, parentheses times parentheses 402, that's just the 446 minus 44, the number of failures, divided by 446, close, divided by the sample size of 446. And we close our square root and we hit enter, and there we get 0.0454, which is our margin of error we calculated here. Then we have to calculate our point estimate. So our point estimate, we take the proportion from sample 1, the 79 minus 438 to get the 0.1804. And the proportion from sample 2, 44 divided by 446 to get 0.0987. We subtract those to get a point estimate of 0.0817. And then we apply that margin of error to it. So we subtract the margin of error to get 0.0363. We add the margin of error to it to get 0.0127. Again, that's what we calculated in the StatCrunch. Like we said, to interpret this confidence interval, add a number line here. We're going from 0.0363 to 0.127. The value of 0 would be way over here on the number line. It's not in that interval. So it is unlikely that that those two proportions are equal. It's unlikely that the difference is 0, so it's unlikely that they're equal. This confirms our conclusion that the e-cigarette treatment is most likely better than the nicotine replacement treatment. What if these conditions are not met? The big one is that there's at least 5 successes and 5 failures for each sample. We could go back and take larger samples, or if this were a more advanced statistics course, There's something called a Fisher's exact test that you could use. We're not going to cover that in this course, but just know that there are more advanced methods that exist if those requirements aren't met. If those requirements are not met, somebody's already taken the data and we don't have the opportunity to go back and resample, we have those more advanced methods that can be used. So that's it for this section. We'll be back to talk about tests for two population means.